Welcome back to this section now. What we are going to start with is the first law of thermodynamics, and we said that the first law of thermodynamics is a statement of conservation of energy. So, energy, whether it is in terms of the heat or the work, it has to be conserved. And so, if you look at the difference between heat and the work, that is the internal energy of the system. So, internal energy of the system, you have to supply both heat and the work. So, if you look at that, then we have to understand in the thermodynamic way what kind of processes we can take the system to, because by providing heat and temperature, pressure, when we are changing pressure, we are essentially doing work on the system. Because when you are pressurizing, the volume is changing. Think about again the cylinder and the piston. When I am pushing the piston in, then the volume is changing, I am doing work on the system. When I am expanding it, then the system is doing work on the piston. So, those are the two situations, the system, the forces working on the system or system working on the environment. So, and you have to first organize your system that way, but if you plot a diagram between pressure and volume, and you start with a point P1, V1, T1 as it is given on your slide, and you go very slowly as we had discussed in previous section as well, so that you can reach the state P2, V2, T2, and the thermodynamic equilibrium is achieved. So, the continuous path is described, the change, then it is called quasi static equilibrium situation, which we had looked at, and it is possible to achieve. So, if you look at this process can be either reversible or irreversible. So, just let us look at the reversible part. In this case, the system remains always in thermodynamic equilibrium and follows a path. So, when it is going in this quasi static equilibrium process and it is carried out in slow enough that it gives enough time for system to adjust to the changes, now this path can be traversed back. Of course, in ideal systems, we are talking about ideal gases, the ideal system, and we are also assuming that there are no frictional forces and the other losses. So, if you look at lossless ideal system, and if you look at pressure versus volume diagram here, I can traverse the same path back, that is called reversible system, and that is shown in the PV diagram. But in other case, when it is irreversible, system goes temporarily out of the equilibrium without well defined value for temperature, pressure and other quantities. So, you see certain fluctuations, you are not given enough time for system to adjust, there is no quasi equilibrium situation. Now, in this case what happens is the temperature may go up, pressure may go down, there is a lot of fluctuation, it is not a smooth path. So, those now if you try to recover that path, you will never be able to, because there will be always more losses or different kinds of losses happening as you try to traverse back, and that is called irreversible system. Although the system has no well defined path in the PV diagram, it ends up in the definite state back in the equilibrium, but if you look at the path that you took is not followed. So, this becomes irreversible system. And if you look at most of the system that you encounter in the world, they are irreversible, because there is always some loss, there is some friction, there are some other gravitational forces which will allow the system to not follow the same path that it went through. And if you have idealized system, there may be some heat loss, there may be some pressure loss, and all of those losses lead to irreversibility, and that is the part that you cannot recover, and that becomes an entropy. So, if you look at here the isothermal compression of an ideal gas, and if you look at this simple system here, V1 let us say it is 0.4 meter cube, P1 is 100 kilopascal, T0 is 80 degrees Celsius, and it is a constant temperature. Now, we are looking at an isothermal system. So, temperature is being constant, but we are changing from V1, we are going to V2. So, we are compressing, this is the compression path for an ideal gas, and because it is a smooth path without fluctuation, quasi static situation, it can be reversible if we are looking at the ideal gases. So, I think now we are going to look at the connotation of the first law and the second law in a very simple virtual molecular dynamics simulation, where we are going to look at the thermal equilibrium in terms of temperature between two systems. And these two systems you are going to look at in a way that they cause us to get to the right temperature. So, let us set up our VMDL experiment again. So, I am back to the VMDL lab, and I am going to go to temperature 3, set that up. Now, let me take you and get to our magnification. So, you can observe all the quantities being changing. So, here we are. So, this is a already done simulation. So, you will see different steps. So, we are going to start in this case, and what I want you to do, observe kinetic energy versus time. So, what you will see that the kinetic energy of the green particle, kinetic energy of the red blue particles, and then how they start with different temperatures, and with the first law and the zeroth law of thermodynamics, the temperature will become equilibrium situation. So, let us start with that. So, if you look at all these particles which we are going here, let me stop here 1 minute, so that you can see the initial positions. Now, at this point all three lines, which is the total kinetic energy line and the blue and green line, are almost at the same place. That means, the system has gone into equilibrium, and if you look at the blue particles are in crystalline phase, let us say solid phase, the green ones are in the gaseous phase. So, let us go back one more time. So, I am going to restart it. Let us go here, create reset averages to 0, start again, pause it. And in this case, let me also increase the temperature a little bit. So, now you can see these are three different temperatures. So, there is a green temperature, and then there is a blue temperature, and the middle line is showing the average between them. So, now as we move forward, what you will see that this temperature is going to go to the same level. You stop here. Now, you can see they are all following the same path. Now, let us go further up in temperature and restart it. Now, again you see separation between the two particles, because these particles are different. So, when I am giving kinetic energy, I am starting with different kinetic energy, but then they are in contact with each other, and as you are also seeing that with the temperature increase, not only the zeroth law is observed, but you are also seeing that there is a melting. So, heat supplied is doing some work on this crystal and changing the shape of the crystal, and that is heat and the work both supplied to the system. So, now let us move forward. So, we are looking at both the first law effect as well as the second law. So, the bonds are breaking, and it is the shape is changing and the pressure is changing, which we can also see in this. So, now at this point we can see the observation of the first law. Now, the temperature has almost become same, and we are looking at that. So, if you look at let us reset the averages again, and but we will start from this point, and let us look at potential energy, see if there is any issue that we can observe in potential energy. So, let us start with this, and now you can see with the color coding that the potential energy is essentially fluctuating, but constant. So, let us do one more thing before we stop this simulation, and we are going to go back again to the very low temperature, almost 0. I restart that, and then what I want to do is I want to pause it and also look at the kinetic energy curve here, and we will see how the particle kinetic energies are there, distribution. Okay, let us stop here. So, it is again adjusting the temperature parameters. So, if you look at and if you follow and if you do this experiment on your own, what you will be able to do that you will be then able to for your own self you will be able to figure out, because all of these particles are now mixed, you cannot see different effects of the temperature between the two, and that is where we say the zeroth law has proven itself, as well as what we can see is the first law is working, supplying heat, so that the melting transition is taking place. Thank you.